This video is for Module 8, Network Layer, for the Cisco Networking Academy Introduction to Networks. In this video, we're going to look at network layer characteristics, the IPv4 packet, the IPv6 packet, how a host routes, and router routing tables. On the network layer characteristics, the network layer provides services to allow end devices to exchange data. IPv version 4 or IPv4 and IPv version 6, and you'll hear me just say v4 and v6 from time to time. Those are the principal network layer communication protocols. The network layer performs 4 basic operations. It addresses end devices, it provides encapsulation, it provides routing, and it provides de-encapsulation. IP encapsulates the transport layer segment. IP can either use v4 or v6 packets and not impact the layer 4 segment. IP packet will be examined by all layer 3 devices as it moves along the network. The IP addressing does not change from source to destination. And there's a note about network address translation, or NAT. It will change addressing, but it will be discussed in a later module. IP is meant to have a low overhead and may be described as connectionless, best effort, and media independent. IP is connectionless, which means it does not establish a connection with the destination before sending the packets. There is no control information needed, synchronizations, or acknowledgments. The destination will receive the packet when it arrives, but no pre-notifications are sent by the IP. And if there is a need for connection-oriented traffic, then another protocol will handle this, typically TCP at the transport layer. IP is best effort. It means that it will not guarantee delivery of the packet. IP has reduced overhead since there's no mechanism to resend the data that's not received. IP does not acknowledge or does not expect acknowledgments, and IP does not know if the other device is operational or if it received the packet. IP is unreliable. It cannot manage or fix undelivered packets. IP cannot retransmit after an error. IP cannot realign out of sequence packets, and it must rely on other protocols for those functions. And IP is media independent. It means it does not concern itself with what type of frame is required at the data link layer or the media type of the physical layer. And IP can be sent over any media type, copper, fiber, or wireless. And finally, the network layer will establish the maximum transmission unit, or MTU. The network layer receives this form control information sent by the data link layer. The network then establishes the MTU size. Fragmentation is when layer 3 splits the v4 packet into smaller units, and fragmentation can cause latency or delay. v6 does not fragment packets. And an example of this means that a router goes from Ethernet to a slow WAN with a smaller MTU, and it would need to break it up. Let's take a look at the IPv4 packet. The IPv4 is the primary communication protocol for the network layer. The network header has many purposes. It ensures the packet is sent in the correct direction to the destination. It contains information for network layer processing in various fields, and the information in the header is used by all layer 3 devices that handle the packet. The IPv4 network header has some characteristics to it. It is in binary. It contains several fields of information. The diagram is read from left to right, 4 bytes per line, and the 2 most important fields are the source and destination. And protocols may have 1 or more functions. There's some significant fields in the v4 header. It'll show you the version. This will be for v4 as opposed to v6, a 4-bit field. The differentiated services, this is used for QoS. The header checksum, the time to live, layer 3 hop count. When it becomes a 0, the router will discard the packet. Which protocol, the source, and the destination. Moving over to IPv6 packets, IPv4 has 3 major limitations. v4 address depletion, which means we're running out of v4 addressing, or we have ran out of v4 addressing. We have a lack of end-to-end connectivity to make IPv4 survive the long as it has. Private addressing and NAT were created to help with the v4 issues. This ended direct communications with public addressing, and the increased network complexity. NAT was meant as a temporary solution, and it creates issues on a network as a side effect of manipulating the network headers and addressing, and that causes latency and some troubleshooting issues. So an overview of IPv6, it was developed by the Internet Engineering Task Force, or IETF. It overcomes some of the limitations of IPv4. Some improvements that it gives, it has an increased address space. V4 is 32 bits, V6 is 128 bits. Now that may not seem like a lot of bits added on, but it's exponential, which means it's a lot more. So it has improved packet handling, it's simplified header with fewer fields, and it eliminates the need for NAT. Since there's a huge amount of addressing, there's no need to use private addressing internally, and it can be mapped to shared public addresses. And for an example here on the legend, there are 4 billion IPv4 addresses, but there are 340 undecillion IPv6 addresses. So we go from this to this. The IPv6 header is simplified, but it's not smaller. The header is fixed at 40 bytes or octets long. Several fields were removed to improve performance, and some v4 fields were removed to improve performance, such as the flag, the fragment offset, and the header checksum. There are some significant fields in the v6 header: the version, which tells you that it's a v6, traffic class, flow label, the payload link, the next header, the hop limit, that replaces the time to live field for the layer 3 hop count, the v6 address source, and the v6 address destination. The v6 packet may also contain extension headers. Extension headers they do provide optional network layer information. They are optional. They're placed between the v6 header and the payload, and they may be used for fragmentation, security, or mobility support. And unlike v4, routers do not fragment v6 packets. So how a host routes. Packets are always created at the source. Each host device creates their own routing table. A host can send packets to the following: itself, 127.0.0.1, or home, which is for v4, or : 1 for v6. Localhost, the destination is the same LAN, and for remote host, the devices are not on the same LAN. For host forwarding decisions, the source device determines whether the destination is local or remote, and the method of determination is, for v4, the source uses its own IP address and subnet mask, along with the destination IP address. For v6, the source uses the network address and prefix advertised by the local router. And local traffic is dumped out the host interface to be handled by an intermediary device, and remote traffic is forwarded directly to the default gateway on the LAN. A default gateway is a router or layer 3 switch that can be identified as a default gateway. Features include it must have an IP address in the same range as the rest of the LAN. It can accept data from the LAN, and it's capable of forwarding traffic off of the LAN, and it can route to other networks. If a device has no default gateway or a bad default gateway, its traffic will not be able to leave the local area network. The host will know the default gateway either statically or through the DHCP in version 4, and v6 sends the default gateway through a router solicitation, or RS, or it can be configured manually. The default gateway is static route, which will be the last resort route in the routing table, and all devices on the LAN will need the default gateway of the router if they intend to send traffic remotely. On Windows, the route print, or netstat -r, displays the PC routing table. 3 sections displayed by these commands: interface list, that's all potential interfaces and MAC addressing, the v4 routing table, and the v6 routing table. Let's do an introduction to routing. What happens when the router receives the frame from the host device? The packet arrives from the gigabit Ethernet interface of router R1. R1 de-encapsulates the layer 2 Ethernet header and the trailer. Router R1 examines the destination v4 address and searches for the best match in its v4 routing table. And the route entry indicates that this packet's going to be forwarded to R2, or router number 2. Router 1 encapsulates the packet into a new Ethernet header and trailer and forwards the packet to the next hop router, R2. There are 3 types of routes in a router's routing table. Directly connected, these routes are automatically added by the router, provided the interface is active and has addressing. We have remote. These are the routes the router does not have a direct connection to and may be learned or discovered manually with the static route, or dynamically by using a routing protocol to have the routers share their information with each other. And then finally, we have default route. This forwards all traffic to a specific direction when there's not a match in the routing table. For static routing, it must be configured manually. It must be adjusted manually by the administrator when there's a change in the topology. It's good for small, non-redundant networks, and it's often used in conjunction with a dynamic routing protocol for configuration of a default route. Dynamic routing discovers remote networks. It means up-to-date information. It chooses the best path to the destination. It finds best paths when there is a topology change. And dynamic routing can also share static default routes with other routers. And finally, we're going to look at the v4 routing table. The show IP route command shows the following route sources. L is directly connected. Capital C is directly connected network. Capital S is static route with manually configured by an administrator. O is OSPF, and D is EIGRP. And the command shows types of routes: directly connected CNL, OD, and etc., and S. So what did we learn in this module? We learned that IP is connectionless. It's best effort. It does not guarantee delivery. The v4 packet header consists of fields containing information about the packet. v6 overcomes some of the limitations of v4. A device will determine if a destination is itself, another local host, or remote host. A default gateway, and this is important because you'll have this on an exam, is the router that's part of the LAN, and it will be used as a door or route to other networks. And the routing table contains a list of all known network addresses. The router uses the longest subnet mask or prefix match. And finally, the routing table has 3 types of routes: directly connected, remote networks, and a default route. These are some of the new terms and commands. There's going to be 2 pages here, so if you want to pause the video here and review these. This is page 2. And thank you for watching the video, and I hope you have a great day.